In this class, we'll talk about the normal distribution and how we use it to interpret test scores and to test hypotheses. The normal distribution is one of the core constructs of statistics. In psychology, education, and other fields, we'll assume that many of the phenomena that we study are normally distributed. So we'll assume that concepts such as intelligence, ability, mood, and memory, or even the errors we make are normally distributed. If we can make that assumption, then we can use what we know to be true about the normal distribution in order to learn about the nature of the phenomenon. The primary way we'll do this is to define the area under the normal curve as the probability of an event occurring. Before we talk about determining probability using the normal curve, let's focus on what we know to be true about the normal distribution. First of all, a normal curve is a symmetrical distribution that is often described as having a bell shape, and hence the term bell curve. However, it is important to be aware that not all symmetrical curves are normal. So in addition to being a symmetrical curve, a normal distribution has the following properties. Approximately 68% of cases fall between plus or minus 1 standard deviation. Also, approximately 95% of cases fall between plus or minus 2 standard deviations, and approximately 99% of cases fall between plus or minus 3 standard deviations. Please note I use the term approximate here. We will explore the actual values a little later. Let's look at this a little closer by taking a look at this example. Let's say we give a test to 1,000 individuals and we find the mean of the test was 30 and the standard deviation was 3. If the scores are normally distributed, approximately 68% of the test takers would score between 27 and 33. Approximately 95% of test takers would score between 24 and 36, and nearly all test takers, or approximately 99%, would score between 21 and 39. Another way of looking at this is that approximately 680 test takers scored between 27 and 33, and 950 test takers approximately scored between 24 and 36. Before going to the next slide, see if you can answer this question. How many test takers scored lower than 21 or higher than 39? The answer is approximately 10. If approximately 99% of test takers will score between plus or minus 3 standard deviations, or between 21 and 39 in this example, then 1% of the distribution will score beyond these points in either direction, and 1% of 1,000 is 10. So let's tie our discussion of standard scores in an earlier class to the normal distribution now. And we do that by considering the standardized normal distribution. This distribution is a table of z-values in which every raw score in a normal distribution is converted to a z-score. Remember, a z-score transforms every score in a distribution to a score expressed in terms of its standard deviation units from the mean. A z-score is computed by the formula you see on this slide, which is z is equal to a score minus the mean divided by the standard deviation. If you'll recall, positive z-scores are raw scores above the mean, and negative z-scores are raw scores below the mean. Once we know how far a score falls above or below the mean, we'll be able to apply what we know to be true about the area under the normal curve to determine the probability of that score or a score greater than that occurring. Okay, let's expand our discussion of the standardized normal distribution by talking about the properties of that distribution. First, we'll define the area under the curve, under the normal curve is equal to 1, or what we call unity in statistics. Thus, the area under the curve that falls above the mean will be equal to 0.5, and because the normal distribution is symmetrical, the area under the curve that falls below the mean is 0.5. If we add together the area above the mean with the area below the mean, we obtain 1, or unity, which is the area under the curve. The range of the standardized normal distribution is plus or minus infinity. In the theoretical normal distribution, the curve never touches the x-axis, suggesting that with any event on the curve, it is possible for an event of a higher or lower value to occur. The practical significance of this is that we are dealing with probabilistic phenomenon in our study of statistics. So we will talk about the probability that something was likely to have occurred rather than saying something is certain to occur. In addition, we won't say we are able to prove something, rather we'll discuss the probability or the extent to which an event is likely or unlikely. In a probabilistic context, we feel confident about our decisions when an event is unusual or unlikely or of low probability. In psychology, we will generally say that an event is usually unlikely if the probability of its occurrence is less than 5 in 100. I'm sure you've all seen in research articles researchers saying a finding is significance and reporting that p is less than 0.05. They are really saying that the likelihood of this event or one greater happening by chance alone is less than 5 in